Want to be the life of an engineering party? Yeah, just bring up the subject of capacitors. Hey, so what do you think about the advantages of tantalum versus niobium oxide for electrolytic? Wait, wake up, stay with me here. Let's talk about some extreme capacitors. You know, the capacitor equivalent of fire-breathing, nitro-burning monster trucks. Let's crank up the capacitance and voltage up and see what happens. Let's get this party moving. Hi, I'm Amelia Dalton, host of Jock Talk. Today my guest is Chris Reynolds from AVX, and we're going to get some fascinating insight and technical lowdown on Hi CV. That's industry slang for high voltage and capacitance. SMD Capacitors. Check it out. And before we get started, don't forget to click that link. There you can find out more information about Hi CV SMD Capacitors from AVX. Hi, Chris. Thank you so much for joining me.
Yep, I'm very happy to be here to talk about capacitors.
So we're here to talk about Hi CV SMD. So how do you define CV?
Well, CV is just capacitance times voltage. And we actually make some very high CV capacitors, 10,000 microfarads at 2 kilovolts. Now, these are not very good for surface mount because you don't get many on a reel. So what we really need to define is high CV per cc. So instead of something the size of a fridge, you've got something that you can get onto tape and reel. So we call, for SMD. So something like a 470 microfarad at 10 volt. That type of range is what we're going to focus on today.
Okay, so how do these different technologies stack up?
If we look at just the basic capacitor technologies, outside of supercaps and just look at the basic caps, you've got electrostatics and electrolytics. Everything from film cap, the MLCC, multilayer organics, micas, and high CV MLCC are all standard electrostatics. They're symmetrical, like the picture on the left at the bottom. Metal plate, dielectric, and a metal plate. Electrolytic capacitors, a little different. You start off with a metal plate and you grow a dielectric. It's directional in the direction of the voltage you apply. So they are polar devices, and these are like tantalum chip, tantalum polymers, niobium oxide, aluminum solid, leaded parts as well, tantalum leaded, and the wet electrolytics as well. That's what constitutes the electrolytic caps. What we're going to do, though, is look at this in terms of power filtering and applications for digital and decoupling. This brings you into the region of the electrolytics and the high CV MLCC for this type of application.
So, Chris, what makes up these electrolytic and electrostatic solutions?
But if we look at the polar electrolytics, they're characterized as an MIS, a metal, an insulator, and a semiconductor. So they start off with a metal base. There's also, in the electrolytic group, OIS, oxide, insulator, and semiconductor. These have got a ceramic-like base, and they don't have any metallic content in them at all. Then there's the electrostatic type, where you actually start with the dielectric and then build up layers of the dielectric ceramic material, put on electrodes, and do a multi-layer type of approach. And the type of capacitors as that relates to, for the metal base, we're familiar with the aluminum, the wet types, or the solid type manganese. Then the chip types with polymer, tantalum, polymer, and tantalum with manganese. There's also a group there for niobium, metal base, but they tend not to be produced in volume commercially. The reason being that you can use niobium oxide as a conductive base for these capacitors and have niobium oxide ceramic-like material for a base, and then niobium pentoxide and manganese dioxide. Then, of course, the ceramic chip we're all familiar with, the standard brick format. And it's these surface mount parts that have similar footprints. They cross over and overlap for footprints, and they have common CV characteristics, cap and voltage, for this type of power application and for digital decoupling.
So how do each of these achieve that same level of capacitance?
Well, just go back to capacitor basics and the good old capacitor equation. The capacitance is equal to the dielectric constant times the area of the plates divided by the distance between the plates. So just taking a wire connected to a battery and cutting it, you've got a capacitor because you've got a hole in the circuit with 2 plates. Increase the capacitance by increasing the surface area, increase the capacitance by putting those plates closer together, and then introducing a material between the plates to increase the field between them for the dielectric constant. And if we look at the dielectric constants of these different materials, you'll see that relative to free space, aluminum's about 9, tantalum's about 27, niobium is getting up to 41, and barium titanate for ceramics is 2,000 on up to 5,000. So you can see here that these dielectric constants, and the MLCC has got a huge advantage for dielectric constant. You also have to remember, though, that you don't get all of these increases in dielectric constant for free. There's some trade-offs. High dielectric constant, you get less temperature stability in general. The higher the surface area, you get higher leakage current. Leakage current is a function of unit surface area. Double the area, double the leakage. And the less distance between the plates, you're going to reduce the breakdown voltage because you're increasing the E field. So you have lower breakdown voltage or lower voltage rating for a higher capacitance.
I see the difference is dielectric constants. So how do these different technologies maximize the area and minimize the distance?
Yeah, so again, if we start off with the ceramic, which is a regular multi-layer component, that area, if you're going to the number of plates we have inside for a high capacitance part, like 100 microfarads with 800 plates, you're talking about 20 square centimeters in something like a 1206 size chip. If we can reduce that distance between the plates significantly, we're going to really increase the capacitance. Or we'll end up with a thin component, as you can see. So that's where embedded components come from as well. They're taking advantage of this thin separation too. Then if we look at solid electrolytics, especially the tantalum niobium family, they start off with a slug with a huge internal surface area in the body, something like 600 square centimeters. And they achieve this by having a powder particle construction where you press a lot of particles together and sinter them, so you have a huge internal surface area like a coral. And then when you grow the dielectric anodically, they grow at something like 20 angstroms per volt that you apply. So some of these 6 volt to 50 volt range, you're talking about 0.03 to 0.5 of a micron. So incredibly thin dielectrics and huge surface area.
So how does this fit in with evolving application requirements?
Well, that's good, because if we go back to the old forecasts we had when we were all young, one of the significant ones we had was Moore's Law. The promise back in 65 was that we'd be doubling every year the amount of floating operation points or the computing power that we could have due to the number of transistors being produced on a die and the speed of the transistors. And that line has just gone on, and it's only been revised a couple of times since. And that has been only because of the infrastructure that supported it. It's no good having something of the computing power of some of the core chips that we have now if you're still using valves for doing the decoupling. So at the low voltage end and the high current end, this technology has really been supported to get us to where we are today. The other end, the high voltage end, the advances haven't been so great. Some of the other technology forecasts we had, we're still waiting for the flux capacitor and enough DeLoreans.
How do these technologies improve capacitance at the low voltage end?
Okay, well, this is interesting. And this is a test question for you. If you memorize that capacitance equation 2 slides ago, if I halve the distance between the plates, what do I do to the capacitance?
Wouldn't that double the capacitance?
Yeah, 4 times. Because what you've done is you've halved the distance, which will give you between each pair of plates double the capacitance. But now you can have twice as many plates in the same volume. So in the same size device, you can have 4 times the capacitance just from halving the distance. And if we go and look at this comparison here, just a cross-section of the ceramic, see how we're making these very thin slurry-type layers now down to the micron level. We're really significantly increasing the capacitance. And these are very low voltage devices, 4 to 6 volts. Now we do the same in tantalum. As tantalum powder technology has evolved, we've been able to use finer and finer grain tantalum. And if we sinter this into a block and have very, very thin dielectrics, then we can have a huge surface area and increase capacitance from the thinner dielectric. So again, 6 volts and 4 volts are taking advantage of really high surface area powders. Now, if you go back the other way and look at the high voltage ratings, you still need coarse grain powders for the higher voltage ratings, because the dielectric, you can't grow that thicker than the grain. So there's a limitation there. So if you look at this chart at the bottom left, what you're left with is, over the past 25 years, we've gone from 6.8 to 22 microfarads at a 50 volt rating, whereas we've gone from 68 to 1,000 microfarads at a 4 volt rating. So you can see the low voltage increase in capacitance is really significant for both of these technologies. And these have maintained lockstep with Moore's law, enabling the new generations of core caps.
Okay, so we've compared the capacitance and voltage for these technologies. What about other considerations?
When we send you a capacitor, we don't just send you a capacitor. You've got 3 resistors and inductors. And this is just a simplified equivalent circuit. Each different technology has got its own ladder network, but made of, resistors and inductances. So each cap is an LCR circuit, and so it will have different characteristics. The materials will give you a temperature difference in temperature characteristics, and the equivalent circuits for the materials will give you the different parametrics. We can start to look at those. If we look at the capacitance stability, the electrolytic family of tantalum and niobium that include the polymers, we've got a very, very flat temperature characteristic over minus 55 to plus 125, 15%. If we compare that with an equivalent capacitance class 2 ceramic, such as the X5R, you'll see it has a sweet spot there, but the capacitance drops rapidly at high temperature, low temperature, and as you apply voltage. So there's a voltage coefficient effect there. Now, aluminum hasn't got the disadvantage of a voltage coefficient, but it does lose a lot of capacitance at the low temperature end. So there's definitely temperature characteristics to be considered here.
So how do they look for frequency?
Again, now, the structure of the MLCC is very regular. You've got equally separated array of plates, metal in, metal out with the electrodes, and so it has a very low ESR and a very fine-tuned impedance, high Q value. So they're like a notch filter. So it has a very characteristic notch for each capacitance value and a very low overall ESR characteristic. Now, by comparison, the electrolytics, such as, again, tantalum and niobium family, that powder and the convoluted internal surface area is actually not a very good network. And so the signal going into coming out through a semiconductor rather than the pure metal is going to have a higher ESR, but also a very broadband response, which is very often desired. So you have a very flat response up to its frequency characteristics of meg to 10 megs. That really constitutes the difference between the two technologies.
We saw the difference with capacitance and temperature. How does the ESR vary?
Yeah, so with temperature as well for the ESR, anything using manganese dioxide has got a negative temperature coefficient. In a power supply, if you cook it, the ESR drops. But at low temperature, the ESR increases. In a polymer, you don't get that increase at low temperature. You get a much lower ESR because it's a conductive material with less resistivity than manganese dioxide, and it also maintains that down into low temperature. And it follows the track of the ceramic, which is going to be a little bit lower than the polymer, and again, with no temperature variation really in the ESR.
So how do these technologies stack up for long-term reliability?
This is interesting because if we look mainly at the tantalum and niobium family, the MLCC, they have no wear-out mechanism inherent in the core materials of the dielectric. So in terms of lifetime, with tantalums, we have to be careful sometimes with early life failures, which we do try and contain those by the voltage aging that we do and the preconditioning we do, so that when we release them, they'll have a characteristic of very, very low ppm failure rate. And with ceramics, they just continue to improve over time. The longer a tantalum lasts, the likely it is to last longer because there's no inherent wear-out mechanism there. Now, for the polymer type, what we've done is we've substituted a manganese dioxide inorganic crystal with a polymer material, the conductive polymer. And polymers do have time dependency. So when you push them to the extreme of voltage and temperature, you can see parametric changes in cap and ESR that are worth being aware of, and they're in the manufacturer's literature. So you can see some slight increases here compared to a standard tantalum.
Okay, Chris, so how does this compare with aluminum electrolytic?
Now, for the polymer, that's interesting. Pushed to the extreme of voltage and temperature, it's similar to the wet hybrid aluminum. But the advantage with the polymer is as you drop the temperature, the lifetime actually increases faster than it does for the equivalent aluminum. So by the time you've got down to 65-degree operation, you're talking about hundreds of years compared to tens of years with no capacitance, no significant capacitance change in the polymer compared to the aluminum.
Okay, that's fine for electrolytics, but what about ceramics? Are there the lifetime concerns there?
Well, the Class 2 ceramics also have got an aging characteristic, which is the opposite that we see with the polymer. You lose more capacitance the younger they are. So the capacitance will drop rapidly. The delta capacitance, which is only, up to 7.5%, will drop more in the first 100,000 hours of operation, and then get to the 10,000, 100,000 hours, you hardly see any significant change. So if you budget for a small capacitance drop in these ceramics for the early operation, you'll be good to go for the rest of the lifetime of the part.
Now, what's the explanation for these differences?
If we look at the dielectric behavior, we taught a standard dielectric model. What happens is in an electric field, a dielectric is an insulator where the electrons in the atoms will align themselves with the field and add to the field. The more dielectric alignment you get and the more electron alignment you get in the atoms, the higher the K, the dielectric constant. Now, that's good for all of these standard, MLCC glass, aluminum electrolytics follow the same pattern as well. But there is one technology that's different.
Okay, so tell me about that one.
This one, although it's just one different type, this constitutes 90% of the world's capacitor usage being a Class 2 ceramic. In that it has the electron alignment in some of the atoms, but it's also got a body-centered cubic structure where the central titanium atom moves in the lattice, and that physical movement also adds to the dielectric constant and gives you this huge dielectric constant. But it comes with some considerations as well. Now you've got something that's physically moving in the lattice. This is the thing that ultimately relates to the properties of limited temperature range for the very high CV X5R. It gives you microphonics. You can actually hear it if you get it oscillating at audio frequencies. This is where the voltage coefficient arises from, where you lose capacitance with voltage. This gives you that aging characteristic that we mentioned. And another consideration is reverse bias ripple heating. If you're operating these parts at a bias, which is how you have to operate an electrolytic cap, keep it always positive, you've got that central atom that's moving a little bit more on the same side. If you take it through zero and reverse the direction, a bit more friction involved there and actually gives you a little bit more ripple heating. So for all of these capacitors, you still have to be concerned about biasing for the optimum application conditions.
Okay, so how interchangeable are these technologies?
Now, that's a good question because we see people that want to go from one to the other or have certain preferences. And actually, they do turn out in the bulk of applications to be very, very interchangeable. The advantage with the tantalum and niobium and the tantalum polymer over the electrolytics are usually size and the lifetime, obviously the low temperature performance for capacitance, good alternatives there. Now, for the ceramics, they're great as well for the capacitance and the bulk capacitance. Sometimes with the ceramic, you can change it for a polymer and get equivalent performance in the circuit. But where you're using that ceramic for very low ESR, you could take a medium CV ceramic, such as an X7R with a wider temperature range, 125 degree, low capacitance, but that will give you the low ESR for the filtering with the bulk cap coming from the tantalum or the niobium. So using these parts in parallel as well is a good way of achieving the same end result.
So how would you summarize the electrolytic comparison?
Well, just as a final summary chart, we have the benefits here. for the tantalum polymer and the niobium Oxicap type. The manganese, there's got indefinite lifetime, high CV per cc, high reliability, mechanically robust and no noise. The polymer has got low ESR. This is how to get the low ESR for the tantalum technology, and it has a more benign failure mode. So if you do experience the infant lifetime concern, it's far less of an issue with the polymer. You don't need to derate it as much because it's got a more efficient self-healing mechanism. So 10% or 20% derating compared to a 50% derate for the standard tantalum. Stable temperature characteristics and no piezo noise. And the Oxicap is a true fail-safe because there's no metal content and it's an oxide base. So you can't actually get a short circuit in an Oxicap. It will break down resistive. It's got great self-healing. It's the highest reliability for a commercial part. You only need 20% derating in this as well. Stable temperature and no noise. If we look at the things that you need to check, the tantalum, always bear in mind that 50% derating as a rule of thumb. The polymer, you have to be concerned about environmental. In the last couple of years, we've got an AEC Q200 capable part, but the commercial parts don't have the same moisture resistance that the standard tantalums do. And for the Oxicap, there's no downside. It's great, except that it's only available up to 10 volt ratings. The dielectric is thicker per volt, and you can't grow such thick dielectrics for higher voltage. So for digital applications, it's a golden technology, but not for high voltage.
What products do you guys have to support these?
Well, we've got lots. What I want to focus on now is tantalum conductive polymer and the Oxicap solutions especially.
Okay, let's start with tantalum.
Yeah, the standard tantalum. If you look in the center there, our TAJ series that we have, all of these parts in general are minus 55 to plus 125. Characteristic of tantalum is that you derate from 85 centigrade to 125 centigrade. We've always had ACQ 200 and an industrial grade. Our THJ was the first 150 degrees centigrade tantalum, which is now 175 as standard, with extensions to 200 centigrade. This is just the commercial offering that we have. We're also doing high-rel versions that we do with full DLA screening up to space level. Very high CV, though, for these applications, especially for wearable applications. We're doing very small size, high-density parts with under-tab leads, and especially for energy, for high joule per CV, for solid-state drives and such like, where we have the under-tab gives you a much denser, more tantalum per unit volume than a J-lead standard tantalum for these type of applications, and very low profiles as well. Low profile has been a pusher. The standard tantalum with the low ESR parts has been a mainstay.
What about conductive polymer?
This is the interesting one. It's been, 15, 20 years of conductive polymer. It's only in the last 2 years that the industry has established an AEC Q200 version. That's because we now have electrolyte materials capable, they're robust enough to withstand these environmental requirements for AEC Q200. We also have, as we do with the standard tantalum for ultra low ESR, we do modules where we have a single chip, but with multi-anodes, with 3 separate anodes inside, which really cuts the ESR down. We also have developing the COTS Plus versions and polymers for space. So really the last 2 years for reliability and environmental robustness has been really a new development in polymers. And the other side of the development for polymers down to 0603 size, down to even 0402 size polymer for wearables is another key driver for these products.
Oxicap?
The Oxicap's an interesting one. It's, again, approaching 20 years of development, and it started off as a standard 105 centigrade product, with the low ESR version being 125 centigrade. But with the low ESR part, the reliability was 5 times that of a standard commercial tantalum, just because we mentioned the differences in the reliability from the field. We do standard and low profile versions and industrial versions, and a multi-anode version, NOM, again, to much reduce the ESR for these parts. And just to finish up on the Oxicap, just to go back over the characteristics and what makes this technology different from the others. As I said, it uses a ceramic base material for the anode, so there's no metal content. It has a more efficient self-healing mechanism. If you break it down in forward bias, it actually breaks down resistive, so it still functions as a capacitor, sometimes with a lower leakage current than a tantalum polymer. So the resistance distribution is great. And the reason for this, it's lower density than tantalum, so the dielectric grows thicker per volt. And the consequences of that is it's a lower electric field stress, which gives you the higher reliability. You've got a higher D. You've now got a thicker spacing between the base material and the electrolyte, but that's offset because it's got double the dielectric constant of tantalum. So you have exactly the same equivalent cap values, 100 mic at 6, whether it's Oxicap or standard tantalum or tantalum polymer. But there is a ceiling on the technology of about 10 volts. But for fit and forget applications in the digital realm, for 5 volt lines, you only need 10 to 20% derating on the Oxicap. It's a golden enabling technology for high reliability digital.
So where does this leave us?
Well, let's go back to our wish list from the 60s. What was the one thing we wanted? We all wanted our own personal communicator. Something you could hold in your hand. You could talk to anyone, anywhere in the world. Well, we've got it now, and one of the last things we do with it is talk on it, So we wouldn't have thought at the time that we could have one of these things, and yet it would do so many other functions. So what do we want today? We want IoT, we want wearables, V2V, AI, all of these things that we want. By the time we get them, who knows what they're going to bring with them? But they're not going to bring anything at all with them without technology from the capacitor and the passive infrastructure keeping up with the silicon.
Okay, Chris, where would I go for more information?
We have full customer support, software, technical articles, design tools, all available through Mauser.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Chris.
Yeah, I love capacitors. I've enjoyed it very much. Thank you.
And before we go, you didn't forget to click that link, did you? There you can find out even more information about Hi CV SMD Capacitors from AVX. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talks section of EE Journal or check out YouTube. Keyword EE Journal.